Class, welcome to the makeup lecture for Wednesday, February 24th, and we're going to continue talking about semantics. So the idea here is we've been talking about semantics and how we can really define what it means to be a programming language. So what are the semantics behind a programming language and how do we know? So we talked about the C scoping rules. So we've talked about that C uses block level scopings and that declarations, right, are valid in the block that they're declared, and they're not global unless they're global declarations are valid for any program that can use them. Otherwise, if the static keyword is used, then the declaration is valid only in that file. So we left on Monday and we saw an example of block level scoping in C. So here we have a function main and we have our block, and here inside this block we have an integer declared. So we have a variable declared that's name is I and type is int. We're setting int to be 10,000, we're printing it out. Then in another block we are printing out the value of I. So we saw that when trying to compile this C program, we get an error where the compiler tells us that, hey, I is undeclared at line 11, which should be this line right here. I is undeclared because even though I is declared up here, this I is valid only for this its enclosing block. So in this other block, we can't access that I in there. So this green brace shows us that this scoping rules that I is valid only within that block. So part of what you should be doing with these examples is I think it would help to try to run these examples to make sure you understand what's going on here in this program. So if we continue, we can look at a different program, very similar structure. We have our int main function, and inside this function we have one block where we declare the integer I, we set I to be 10,000, and we print out I. In the second block, we define we declare an integer I, and we print out the value of I. So now the question you should be asking yourself, okay, how does this change what we had in the previous example, right? The previous example had there's only one line that's been added here, and that's the declaration of int I right here on this line. So now we want to think, okay, is this program going to compile? So if I compile this program with GCC, is this program going to compile? So those are the type of questions you should be asking yourself. So you should be thinking, A, is this program going to compile? B, if it's not going to compile, is it going to have the same error that it had in the previous example? Same error or different error, right? That previous example said that, hey, this I is an undeclared identifier. So if we think about it, okay, and we try this, we can see that, okay, this program does compile correctly, and then this creates an executable program called a.out. We can execute a.out. So now the question in your mind needs to be, what does this program output? So what is the output of this program? And this is a good self-check of your ability to understand and interpret C code and C semantics. And this is going to be important information that you're going to need for midterms and finals, because you're going to be looking at a lot of code and having to simulate its execution by hand by that big, beautiful computer called your brain. So let's step through this, what we think should be executed. So we have in this first block, we have the I is declared. We set I to be 10,000. And so we're going to print out, we're going to print out 10,000 and a new line. Then when we enter this next block, we have a new I. We're going to print out I. But now the key question is, what is this I value that's going to be printed out? Is it going to print out 10,000? Is it going to print out something different? And so let's see one execution of this. So one execution, it prints out the 10,000. That's the wrong number of zeros there. That's 10,000, that's 100,000, but it should be 10,000. Then it's going to output 0. So this other printf is going to output 0. So you think, that's weird. Why did it output 0? So, knowing what we know about programming languages, right? So we can know that this int I here, so the key thing is when resolving this identifier I, we want to resolve it to the closest declaration to this value. So we know that this I refers to this declaration of I in this block. That means that what happened to this I in this block, even though it has the same name, right? These are different declarations, which means they are considered different variables and should be completely separate. So that setting I here to be 10,000 has absolutely nothing to do with this I over here. And that's a key point that I want you to be thinking about is, okay, they may have the same name, right? But they actually refer to different declarations, which is why they're different and why changing this I has no bearing on this I in this other block. So now back to the question of, okay, what is being output here with this 0? And it turns out that, well, if we look at this block, right, there's only 2 lines, so it's pretty easy to reason about what's going on here. So we have a declaration of a variable, and then we're printing out that variable, but we've never initialized I to any value. So what we have here is basically a case of an uninitialized variable. And so we're going to need, so C allows this, and maybe the some of you have noticed, or maybe you can notice now that I didn't add the $W all flag here to GCC to show all warnings. If I had, it would have told me that, hey, there's a warning here because you're using I before it's initialized. But that's not an error. That's not a compile time error. That's actually not even a semantic error according to the program. What it is undefined behavior. So the spec does not say, in C, the specification does not define what the value of uninitialized variables are. And so the implementation is free to do whatever it wants. So in this case, in this first example, was run on a CentOS 6.7 machine. So here it outputs 0. But if we run this on my Mac, which is actually going to use a completely different GCC, it's actually going to use Clang under the hood, not GCC, but that doesn't matter. We can compile it. It's hopefully going to compile just fine, right? So if it's a valid C program, it should compile both on Linux and on Mac. And so once it compiles, when we execute it, it's going to successfully output 10,000, as it should. Yay! And then it's going to output, whoa, some other junk. What is that? 669,615,670. Okay, so wow, completely big difference. But we can see here we've actually done some behavior that the specification does not define. Therefore, it's completely okay from the semantics of C that this program, when run on the same C program, when run on 2 different operating systems, outputs different values. Because the output of an uninitialized variable, the value of an uninitialized variable in C is not defined. Okay, and then as we get closer in, I think we'll actually get into what's being printed out here. But for those that are curious, it's essentially whatever was on the stack at that point in the program's execution. So for whatever reason, maybe because differences to stack layout, something 0 is printed out in this case, whereas this other value is printed out in this case, which is probably some sort of address, is my guess. Okay. So now we've seen examples of C scoping, and we've seen examples of C block level scoping. Now, the real question that we want to try to answer is, right, this duality of declarations, right? So the semantics of how long a declaration is valid for, right? The flip side to that is, how do we resolve a name? So when we see an identifier, we need to be able to map it to the declaration. Right? And this is critical because we know that every use of a declaration is going to be the same variable, right? So this is what's important, right? The name alone does not tell us that it's the same variable. Just as we saw in the previous example, we had 2 different variables called I, right? Exact same name, but affecting one didn't affect the other, even though they had the same name. And this is because the important thing is the declaration, not the actual name itself. So resolving a name is key. So when we see that identifier, when the compiler sees the usage of ID or I, how does it map it back to that declaration? So the compiler does this using a data structure that's called the symbol table. And this is a very simple table. It basically maps names, right? So it maps names to declarations and attributes. So what would be a declaration? Well, we saw. So we'd see that, hey, this is the I on line 1, 2, 3, 4, 5, and this is I on line 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, on line 10. And attributes would be any additional information about that declaration and that name. For instance, attributes can be types. Attributes can be class attributes, so visibility symbols. Attributes can also be, is it a function or is it a value, right? Or is it a pointer, right? All these things are additional attributes about a declaration. So when resolving a name, there are two types of scoping rules that are used. And one type, which is the type that you're most familiar with, so this will probably be pretty natural for you to understand and to use, because this is how you're used to thinking about programming languages. So static scoping rules, the basic idea is you resolve a name to a declaration statically. So you can actually look at the code just like we were able to look at those C examples, and you can match up usage of an identifier, usage of a name, and you can match it up to that declaration. And in essence, what this means is that the compiler creates the symbol table, and it does it statically while it's compiling the program. So you can think of that the compiler is going through the parse tree, and whenever it sees a new scope and new declarations, it adds those declarations to its symbol table. And then when it sees identifiers, it looks up in its symbol table, hey, do I see an identifier in my symbol table? If so, then I know how to treat that name, right? And so this is why this symbol table is really important to compilers, and this is exactly how the compiler is able to tell that you have an unidentified, an undeclared identifier error, because it sees an identifier, right? And we've actually seen how to define an identifier. It's defined using tokens. So in the parse tree, as it's going through the parse tree, when it encounters an identifier, it's able to say and look up in its symbol table and say, I actually have no recollection, I have no entry for this name in my symbol table, therefore this must be an error. This has to be an error. I can't compile this program. It may be syntactically correct, but it's semantically incorrect. So the flip side of dynamic scoping, which we're going to get into, is that the resolution, so the idea is this mapping of names to declarations actually changes dynamically when the program executes. So the idea is, instead of the compiler creating this symbol table statically while it compiles the program, the symbol table is actually going to be created dynamically at runtime, and this lookup mechanism is going to happen off the bat. This lookup mechanism is going to happen right away. So let's go back to our notes. We're going to look at some examples here. So we're talking about static scoping rules. So the first key thing to understand is that scoping rules are hierarchical. Blocks are hierarchical, right? There's nested blocks. So if we label this as block 1, and then inside there we have another block, and I have some if condition. I'm going to put dots in there because I can't think of what to put in there, right? But this would be block 2, block 3, right? So by looking at that, we can see that there's a parent-child relationship between 1, 2, and 3. So if we were to draw this static scoping as a tree, we'd have something like, okay, 1, and 2, and 3, right? So I know that 2 and 3 are both siblings, and then if there are any blocks, let's say inside 3, this would be 4, and so on. So at each of these blocks, variables can be, in each of these blocks, variables can be declared, right? So let's take in this example, so the question is, okay, let's say here in block 1, and here I'm going to use this kind of abstract tree structure for right now, so I don't have to just write out a program and have everyone yell at me because it's not a valid program. So let's say we have an integer I, right? We have an integer I declared here, and in 2 we have int x, 3 we also have int x, and in 4 we have an integer called I, right? So these are all declared, so it should be fairly trivial, and one thing you can do to check yourself is say, can I take this tree block structure and turn it into blocks like this, right? You don't have to worry about this if statement, but it should be pretty clear here. So now to do static scoping, right, and to resolve a symbol, so let's say inside block 2, right, inside this code here, it's a terrible arrow, inside this code here I have, we'll say x is equal to x plus 1, right? And you can think about actually what we have here is a tree, the parse tree for this, but for right now we can not think so concretely in that terms, and we'll deal with the code that we're used to thinking about. So the compiler sees this x, right? And so we can think of, okay, it's already tokenized, the lexer has already tokenized this, so it's turned this x into the abstract token ID. It's created a parse tree out of this. The parser has created a parse tree, so there's a node that's called an ID. But I have, as we've seen in our lexer, we store the value of this token, right? So we'd have ID and the string x, right? So now when I'm going through and I want to check the semantics, I say, okay, how do I map this identifier x to a declaration? Is it a global? Is there some global int x? How do I do that? So what I'm going to do is, starting in my current block, I'm going to look up in my symbol table and say, in my block, and say, okay, is there an x declared in my block? And here I say, yeah. So I see, okay, yeah, bang, that right there, that's good. If it's not in my block, then I go to my parent's block. And I say, is there if it wasn't here, I would say, is there an x declared in block 1? And then if that's not true, then I would keep going up and up. So for instance, in 3, right? So if we have right here, if I say I is equal to I plus 1, so let's do something else. Let's do x is equal to I plus 1. Right? So when I get to this I want to resolve this name I to a declaration. So I would first look in block 3 and I say, okay, is I declared in block 3? And I say, well, no, clearly the only thing here declared in block 3 is int x. Now, note, right, I'm in 3, I haven't entered block 4, so this int I has no bearing on it. We don't even look at our children. We look at the parent and say, okay, it's not in 3, so let's look at the parent of 3. Okay, here in block 1, is there an I? And I say yes, and so I can map that I to that declaration. But in 4, right, and the same thing with this X. I can map the X. I first look in block 3. If it's not in there, I look in block 1. Now in this 4, now if I see an I, when I look that up, which block do I look in first? Well, following the same pattern, I look up in block 4. And I say, is there an I declared in block 4? And we say yes. So this I refers to this declaration of I. So note that we have 2 names, right, in 1 and in 4. But this one refers to this I, and this refers to this I. So let's look at an actual example of a program. So here I have a block. Okay, I have an integer I. I set I to be 10. These are all braces. Sorry, my braces game is kind of sloppy right now. So here I have an integer x. I set x to be 10. And then here I say x is equal to x. Let's have an integer I. I is equal to 100. X is equal to I plus x. Okay. Close, 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 close up here, close up here. Right? So this hierarchical nature essentially means that, so here we just have, so if I draw this, I have 1, 2, 3, right? And all of these scopes are nested within each other. So there's a parent-child relationship here. And in here, I have an int I. In block 2, I have an int x. And here, block 3, I now have an int I. So this use of I can see is in block 1. This line of code is in block 1. And this line of code is going to change this variable and set this I to be 10. So we'll just add the value here. And then I'm going to execute this, and I'm going to say, okay, how do I map this up? Oh, that maps over here, so this is going to set this x to be 10. And then I go here, I say, okay, which is this I? Well, I just look at this chain, and I see, oh, it's this I. So I'm going to set this I to be 100. And now here, when I say x is equal to I plus x, I'm in block 2 now. I've left block 3. I'm in block 2. And so now I'm going to say, okay, x is equal to I plus x. So i's current value is not defined in block 2. Defined in block 1 is 10. X's value is 10. So I'm going to say x is 20. Yeah, that is 10 plus 10. Good math. But note that I didn't say x is equal to 110. Right? And that's the key thing. So this I essentially, what we call shadows this declaration of I. Because there's actually no way I can reference this outer I once I've declared this inner I variable. Okay. So then let's look at a more complicated example. So here we're including our standard io.h function, so we get access to the printf functions. We declare an x. And so SelfCheck, how far is this, how far is this scope valid? How far is this declaration valid? And so the answer is, well, it depends on what our semantic rules are. So I'm telling you we use C style semantics here. So this means that this is a global declaration of int x. And so x is valid from here to the end of actually the program. So any other files can include this x. But right now we'll just focus on this file, assuming this is a standalone file. So then I have another one. So then if we were in class, I would say, so is this a declaration? And we'd have a discussion about it. And so hopefully you can convince yourself that yes, this is the way you declare. So what am I declaring here? Well, I'm declaring, so the first thing is, what is the name of the thing I'm declaring? And you can see by my highlighting that the name is bar. But the idea here is that I'm declaring that there is such a thing called bar. And what is the type of bar? So here, just like in this previous declaration, I'm declaring a variable x, and I'm declaring that x has type integer. Just as here, I'm declaring that there's a thing called bar, and bar is a function, right? So what is the type of that function? Bar is a function that takes in no arguments, which is indicated by the fact that there's nothing between the parentheses, and it returns nothing. So it returns void, nothing. But the key difference is with the semicolon here, this is bar without a body. So I'm saying there exists a function called bar, and here are the parameters, here are what it returns, but I don't know where the body, like I haven't actually defined the body yet. So this is just a declaration. We're just declaring that there is a function called bar, but we're not necessarily saying where it is or what the definition is. The flip side of this is I can declare and define a function, right? And so this should be pretty natural in C and in your programming. And once again, the point is not to reiterate simple concepts, but to get you to think more deeply about the current things that you already know. So, and inside this function foo, so here, now with these braces, we've started a new block. We've started a new scope. So inside this scope, we define a character C, and we set it to the character C. Then we call bar, and then we print out the value of x and the value of C. So, important thing to note, even here. Where is this bar resolved to? Right? It's saying, well, remember, when we're doing resolutions, we're trying to map names. So here, the name bar. We're trying to map bar to the declaration where it's declared. Right? So this bar would map to this declaration here, just like this x maps to this x here, and this C maps to this C here. And we can define other functions. Let's call it baz. Baz prints out the value of x and sets x to be 1,337. Now we have the body of bar, right? So this is the function bar. Inside this function, we set x to be 100, and then we call baz. So finally, we have our main function where we set x to be 10, then we create a new block, we define a new variable, right? So let's pick this declaration apart based on the semantics. We're declaring a variable whose name is x, whose type is char star, and whose value is initialized to the string testing. And then we print out x. If you don't understand the printf directives here, like %s, %d, and %c, you should spend time studying what these directives do and what they mean. This is something that I noticed last semester that tripped people up, is not even knowing what simple printf style things actually print out. As far as complication, I don't think you need to know too much more. That's anything more complicated than that, but you should be familiar with printf. I mean, this is one of the core bedrock kind of functions. So after here, then we call function foo. So first thing you can do is check yourself. So so on an exam, right, I may give you some code like this, and I might ask you, hey, what does this program output? Right? It's not an outrageous question. I think it's something that you all definitely can do and you should be able to do. But, so that's one step, right? It's, okay, what does it output? But two is, okay, well, what are some strategies that I can use to actually do this, right? And so one thing can be, okay, let's try to think about for every one of these declarations, what is the length of this program that it's actually valid, right? So what's the scope of all of the declarations in our program, right? So more self-check, right? So what is the scope of X? Well, based on the semantics that we've been discussing for C, right? X is a global variable, so it's going to be, its scope is from its declaration all the way to the end of the file, right? We're going to say int X exists all the way here. And so what about bar, right? How far is bar declared? What's the scope of bar? Well, it's from here, right after it's declared, all the way to the end of the file. And so this is the key thing. If you've ever wondered, gosh, in C, why do I have to declare these functions before I call them? Like, it seems silly. Can't the compiler go through and figure out all of my functions and then allow me to do this? And the reason is, yes, it could do that, but the semantics of C means that it really, that's not how C programs work. C programs work that a name, an identifier, a declaration is valid from where it's declared to the end of the file for global variables. And so this is why you have to declare a function bar if you want to call bar in a function foo before you have the body of bar, right? And this is also how you resolve mutually recursive functions. You have to declare them before you use them. And in case you're wondering, well, but then how do header files maybe mix into this? Well, you put these declarations inside the header files, and you'll notice that header files always go first, right? So inside standardio.h, there is a declaration and definition of the printf function. And this is how we're able to use and call those functions that are defined in standardio.h. Okay, then moving along, right? So once again, the difference between this bar and foo here is bar is declared here, whereas foo is declared and defined. So we have the body of the function foo here, and also a declaration of a function called foo. And so foo is going to be valid from here to the end of the program, right? And so this is actually, if you think about, well, shouldn't it be after this declaration here, like after the end of the function foo? Because that makes sense, right? Bar is declared pretty much after the semicolon, right? Anywhere after can call bar. So shouldn't it be the case that foo is valid, the scope is in effect after it's defined anywhere down there? And the problem you get in there is, okay, this foo, well then foo can't call itself. It can't be a recursive function. So that's why the scope of foo actually extends inside of its own body so that you can have recursive functions. Okay, then let's step into the body of foo. So important note, right? So that here foo has its own block, right? The body of foo has a block, so this is a new scope. So now, when this char character C is declared, right? This means that where's the scope of C? Does the scope of C extend all the way down? Can we access this C from main? Can we access this C from Baz? Because they're next to each other, maybe because they're neighbors, we can do that. So we know from the scoping rules of C that it's just in this block. So C is going to be valid just in the block that's inside foo. And here in bar, right, X is going to be valid just inside this block. And here in this X, this character pointer X is just going to be valid inside the block that's inside main. So now that we've done this, we've identified the length and the scope that all of these are valid, right? You can see that actually if we turn this whole thing, let's see, angles 270, if we rotate it 90 degrees counterclockwise, right, we can see we have our nesting scopes, which is what we were just drawing on the notes, right? We have the global scope, and in the global scope, X, bar, and foo are declared, and then each of those has sub-children scopes, right? So this global scope has several sub-blocks and sub-scopes where C, X, and X are declared. So this means when the compiler's going through this code, and when it encounters something like, right, so convince yourself that this first instance of bar here is actually the first usage of a name in the program. So here we have, in a parse tree, it would be bar, left bracket, right bracket, or left parentheses, left parentheses, right parentheses. So the idea is now the compiler sees this and it wants to go, okay, what is bar? It's just a name, right? I need to look up what that name means. So it's going to look it up in the scopes just like we saw, from the current scope to its parent scope to its parent scope, until finally it either finds it or it doesn't find it. So it's going to look up bar in this local scope and see, nope, no bar defined in this local scope. And then it's going to look it up in the global scope and it's going to say, aha, this bar maps to this declaration of bar right here. Awesome. Then it's going to see this X. And it's going to say, okay, which X does this refer to? Well, look in the local scope. Okay, no X here. And then look in the global scope. Hey, there's an X defined. So I know that this X refers to this declaration of X here. Or as I've written it here, including the length of X's declaration, this is where X is defined. And then it looks up C, and it says, okay, is C defined in my local scope? Yeah. So that means this C refers to this character C right here. Great. Okay. And then when we get to the printf, right? Printf is just a name. It's no different than bar or X or C, right? It's just a name that the compiler still has to resolve to a declaration. And it will actually resolve it to a declaration in standard.io.h, so we can actually not worry about that. Okay, moving along in Baz. So now when we get this X, we say, okay, is there an X in the local scope? No. Is there an X in the global scope? Yes, it refers to that X. And so the same thing with this next X here, right? On the next line, we'll see that this X refers to this same int X. And down here in this X, right, when we say X is equal to 10, well, the question is this X going to be point to this X because they're like close by, right? And the answer is no. The exact same process occurs. We look for X in its scope, which is from here to here. We say, is there an X declared here in main? No, there's no X declared here in main. Therefore, go to the global scope, the parent scope. In this case, the parent scope is this X. And so it won't point there. It's not going to point to this character pointer X. So why? Well, this scope is a child of our current scope, but we only look in the current scope and then parent scopes. We never look in children. So this X actually resolves to the global X. But inside this block, when we see this name X, we need to resolve it to the declaration. So we say, okay, what is this X? Well, look in the current scope. Is there an X? Yep. There's a character pointer X, and so that refers to this X. So we can see that this X here, right, has two completely different meanings. In one case, this X is referring to the global declaration of an integer X, and in this other case, this X is referring to an X that's declared in the local scope that's a character pointer. So two different types, same name, but still everything works. And the important thing is that we can know and we can look. So what happens when we compile this? So question you should ask yourself, is it going to compile? Are there any errors? No, yes, yes, no. Okay, it compiles fine. then what happens when we run it? What's it going to output? So here's where you have to then be able to step through this program and be able to simulate the execution, right? So if we step through here, right? So the first thing to ask yourself is, okay, which function is going to be executed first? Well, it's clear that main is the function that should be executed first. That's the C standard. And so when function main is executed, the first thing that happens is x is going to be 10. And so we've already resolved this x, right? So before execution, we've gone through that process and we said, okay, this x refers to this declaration of x. So this global x now has the value 10. Then we enter this block. We initialize a local x to be the string testing. And so we print out a string. %s means print out a character pointer string. And we print out this x. This x refers to this local x, which we just did. And so it's going to print out testing followed by a new line. Right? So the first line of output is testing. Then foo is called. So we call foo. Foo sets a character C to be the character C. It then calls bar. Bar declares a local variable x to be 100. And then we call baz. Baz prints out the value of x. So what's the current value of x? It's 10. Right? This call to main set out 10. Please check with yourself to make sure you understand why it's not 100. Right? So we print out 10. Then we set x to be 1,337. We return from baz to bar. We return from bar back to foo. And then we print out, okay, we first print out %d means take that value, print out as a decimal. So we print out x, so x is 1,337 because this x refers to this global x. This x also refers to that global x, so we need to print out the value of that declaration, of that variable. And then we print out a character, so then we print out C, right, from this C. So we should print out first 10 from our first line of baz, and then we print out 1,337 and C. Right, so you should be able to do this, and this is something you should be able to do. You should be able to take code, look at it, and really try and understand, okay, what are the static scoping rules here? So in static scoping, we're creating these symbol tables of, okay, in this scope, these variables and declarations are declared. But when I already did this. So in dynamic scoping, the symbol table and the current scope is changing and updating at runtime. So the idea is when we're trying to resolve a name, a specific variable name, let's say x, we actually look up dynamically at runtime in the symbol table for the last encountered declaration of x. So what does this mean in practice? In practice, it's kind of crazy because this means that x, this name x, the declaration could change, the type could change depending on how a function is called, right? So actual languages actually use this. So Common Lisp actually allows both dynamic and lexical scoping. So let's look at an example to kind of help try to illustrate this point. So before we were able to completely create essentially this tree or these symbol tables dynamically, right? We were able to look at the code and be able to create these symbol tables, right? That's where the static part of static scoping comes in. We only think about these things statically. We only create these, we can create these symbol tables statically and we never have to think about them because they never change. Okay. All right, and to make the example, I I guess I'll be consistent. All right, printf d slash n x Okay, I have in my main, I'm declaring an integer x, I'm setting it to be 10,000. I call foo. I set x to be 10. And then I'm going to call some other function bar. And then I call foo. Right, so even just looking at this, let's not talk about bar for right now. Let me get rid of some of this. So, here in this example, we're declaring a global integer x, and we're setting it to be equal to 10. So, if we're talking about static scoping, right, just looking at this x, if I construct this symbol table statically, I say, okay, I want to resolve this x. I have to look in the local scope of foo. There's no x declared there. Therefore, I have to look in the global scope, its parent, which is the global scope, and I see, aha, this x refers to this global x, right? And that's the important point. It always refers to this global x. It doesn't matter how or where foo is called. This x always refers to that x in static scoping. But in dynamic scoping, that's no longer the case. So in dynamic scoping, we actually keep track of the symbol table as things are executed, right? So we first execute this instruction, and so we create an entry in our symbol table. So here we have, let's say, name value for now. So the name here is x. The value is currently 10, right? So this is the global scope. So we execute this. We execute this. So what's this going to do? How's this going to change our symbol table? Well, we're defining a new symbol called foo. Its value is the body, right? It's a function. I didn't include other stuff here. And then I get here, right? So I create a new symbol in my symbol table called main. The value, we're going to say, it kind of points to this guy. Right? And what happens when I get to this integer, this main function? Right? Well, I'm going to start executing it. So I execute this first line. But first I've entered a scope. Right? So this right here is my global scope. And now I have a child scope of this global scope, right? I've entered a block, and then see I've done that. So I'm going to illustrate that here, and I'm going to delete these pointers because they're kind of annoying. I'm going to illustrate that here with an arrow. And so now I start creating a new symbol table, and I start updating it. And now I say, okay, int x. Great, I know how to deal with that. I create a new entry in my symbol table called x. The value of x is 1000. Great. Everything is awesome. Okay. Then I execute this next function. So this is going to call foo. So when I enter function foo, notice I've added now a new block here. Right? I've entered a new block, so I create a new scope of the symbol table. But there's no declarations in foo, right? So this is empty, which I will kind of do like this. And then we see, okay, now we see the x. And we need to resolve x back to the declaration, right? Actually, right, at this point, we're actually executing the program. So we're trying to say, okay, what is the current value of x so that we can print it out? Well, I take this x, and what I do is I look essentially up the symbol table, right? And I say, okay, is x in my local symbol table? Nope, there's nothing in there. So go to the parent. Okay, is x here? Yeah, x is here. So the value of x right now is 10,000. So it's going to print out, if I execute this, it'll first output 10,000. And then after this executes, we are leaving the block foo, so this goes away because everything that was declared in foo is only valid for this specific block, so we're going to completely get rid of that. Then we're going to return from the function foo, and when we return from the function foo, we're going to now go to this line, and this line is going to say, okay, look up this x. Which x's value am I going to change? Well, look up in your current scope. Okay, the current scope in the table is here. Oh, great, an x is here. Set this value to be 10. Perfect. Okay. And I'm going to just in time write a function bar. And I'm also going to just in time delete parts of the code. Okay, so when we get to this function bar, we start executing bar. When we get to bar, right, we create a new scope because we've entered a new scope of the program. And we say, what are the declarations in here? Okay, we've declared a variable x. X has the value 42. We see a function call. We go to function foo. We create a new scope, right? We've entered a new block. The scope has no declarations. And so now, right, we get to x, and we need to resolve x again. And we say, okay, what is x going to output? Well, we look up x, we look at it in our local scope. There's nothing there, right? So remember, we go up. So we look here. Nope, nothing here. We go to the next scope. We say, oh yeah, there's an x. Great, the value is 42. So output 42. So you can see that this x, if we look at it here, right, the first time that we called it, it actually resolved to this declaration in main. But the next time we called it, it actually resolved to this declaration of x in bar, and in fact, it never ever referred to this global x for whatever reason. When statically, it would always print out the same, it would always look at this value, it would print out 1010, right? And so this is the key idea behind dynamic scoping, is this resolution, and the resolution is done at runtime, and the construction of the symbol table is done at runtime. Okay, so on Friday we'll go into more examples of dynamic and static scoping. Thank you so much for taking the time and hanging out with me on this amazing Monday afternoon, but for you, due to the amazing time traveling abilities I have, you'll be listening to this as early as Tuesday or Wednesday. So anyways, I've missed you all, and I look forward to seeing you on Friday.